Revolutionizing quantum machine learning. LANL's breakthrough with Gaussian processes. The quantum computing revolution just hit a critical roadblock, and the solution might rewrite the rules of machine learning itself. For decades, neural networks have driven breakthroughs in classical computing, from AI chatbots to autonomous vehicles. But when scientists tried to transplant these systems into quantum machines, they stumbled into a maze of unsolvable problems. Now, a Los Alamos National Laboratory LANL team claims to have cracked the code using a surprising mathematical shortcut, Gaussian processes. And this discovery could redefine what quantum computers are capable of. In a groundbreaking paper published in Nature Physics, researchers revealed they've proven that quantum systems can harness Gaussian processes, the same statistical bell curve principles that underpin modern AI. Here's why this matters. Classical neural networks work by aggregating millions of guesses from artificial neurons, which eventually align into a predictable Gaussian distribution. The LANL team showed this statistical magic isn't limited to classical computing. It applies to quantum systems too. But here's where it gets controversial. For years, scientists tried forcing quantum computers to mimic classical neural networks, only to hit barren plateaus, mathematical dead ends where learning grinds to a halt. We were copying outdated blueprints, admits Martin LaRocca, a quantum algorithms expert on the team. Quantum machines don't play by classical rules. We needed a fresh approach. Their solution? Ditch parametric models, like neural networks, for Gaussian processes. Unlike neural networks, which tweak millions of parameters to learn, Gaussian processes use probability distributions. Think of predicting housing prices by updating a bell curve as new sales data arrives. The team mathematically proved this method avoids quantum computing's notorious pitfalls while retaining predictive power. This isn't just theory, it's a toolkit for the quantum future, says lead author Diego Garcia Martin. Imagine training quantum systems to model climate patterns or drug interactions by continuously refining predictions, much like updating a home price estimate. The catch? Gaussian processes only work if data follows that bell curve, a limitation the team overcame with rigorous mathematical safeguards. But here's the twist that's sparking debate. The LANL team argues quantum researchers should stop retrofitting classical models and instead build new frameworks from scratch. We've been beating a dead horse, says lead scientist Marco Cerezo. Quantum machines need quantum-native solutions. Critics might ask, are we abandoning neural networks too soon? After all, they've dominated AI for years. Yet the team's results suggest Gaussian processes could unlock quantum machine learning's true potential if the field embraces this paradigm shift. With quantum computers still in their infancy, this work lays theoretical groundwork for a future where they tackle problems no classical machine could solve. But it raises a provocative question. Should the quantum community cut ties with classical methods entirely? The paper, funded by LANL's pioneering research initiatives, challenges researchers to rethink everything. As Cerezo puts it, the quest isn't to mimic the past, it's to invent what's never existed. So what's your take? Is ditching classical neural networks a bold leap forward or a risky gamble? Let's debate in the comments. Quantum breakthrough. LANL's new path to quantum machine learning. A team at Los Alamos National Laboratory has made a groundbreaking discovery that could revolutionize quantum machine learning. They've developed a new method to bring the power of Gaussian processes to quantum computers, sidestepping the issues that have plagued previous attempts to adapt classical neural networks to the quantum realm. This opens up exciting possibilities for solving complex problems that are currently intractable, even on the most advanced classical computers. The key breakthrough came when the researchers realized that large neural networks converge to Gaussian processes, which follow a bell curve distribution. By proving that the same principle applies to certain quantum computing processes, they've unlocked a powerful new tool for quantum machine learning. But here's where it gets controversial. The team argues that researchers should stop trying to force classical models into the quantum world and instead focus on developing entirely new approaches tailored specifically for quantum computers. This provocative stance challenges the conventional wisdom in the field and is sure to spark debate among experts. The implications of this work are far-reaching, from enhancing artificial intelligence to tackling previously unsolvable scientific problems. As quantum computers continue to advance, this new approach to quantum machine learning could prove to be a game changer. But what do you think? Should researchers keep pushing the boundaries of adapting classical methods? Or is it time for a radical shift in thinking? Let us know in the comments.